Hello friends, in continuation to the previous sessions wherein we learned the basics about the control engineering as a subject, we went on to know about what is control engineering, where we find the applications of this particular subject and why it is very important for an engineering graduate to know about the construction, the insight and the design aspects of any control system. Apart from that, we went on to know the various different types of control systems are available. Mainly we went on to know about what is an open loop control system, what is a closed loop control system with lots of examples. In open loop control system, we went on to know in detail about the working of an ordinary bread toaster with the perspective of the control system itself. And we went on to illustrate the definition of open loop control system, that it is a kind of system wherein the output will not influence the input. And we went on to know with the example of the ordinary bread toaster itself, wherein the degree of darkness that we actually avail after the bread has got toasted, it is not going to influence in any case if the bread toaster is not working fine and you don't get the bread toast as per your desire. You are not finding the desired degree of darkness on the bread toast, then there is no mechanism wherein it can tell the timer of the bread toaster to correct the timer so that you get the desired degree of darkness on the bread toast. That is not happening. That is why it is called, it is an open loop control system. Like that, we went on to illustrate the definition of open loop control system on automatic washing machine, electronic iron box, as well as the microwave oven. And there are hundreds and hundreds of systems which are around us, which according to the definition could be addressed as open loop control system. And then we also went on to know the closed loop control system. What is the closed loop control system? The definition of closed loop control system we learned, wherein it says that it is a system wherein the output has an influence on the input, right? So how? With the presence of output measurement device as well as the feedback element. We also went on to know the examples also with the manual water heating system. And then we also got to know about manual speed control system, and we also took the examples of ship stabilization system as well the missile launching system. There were, with the help of the block diagram circuits also, we learned how a block diagram represents any control system with those examples that I have just now mentioned. Now, in the closed loop control system also there are several types. So, the classification of control system is in two major types. One is the open loop control system, the other one is the closed loop control system. In the closed loop control system also there is a classification. What is that classification or the types? There are three types of closed loop control systems. Number one, regulator system. Number two, follow-up system. And number three, the servo mechanism. We will now try to learn those three types of closed loop control system in detail. What it means to say by a regulator system, by a follow-up system and by telling some system as a servo mechanism. Now, if you just look at the regulator system, the regulator system is a kind of closed loop control system wherein the input does not vary with respect to time. The input is not going to build with respect to time, right? So, this is an example, a home heating system, wherein what is the input to the home heating system? It is only the desired temperature. Suppose we want only about 22 degrees centigrade to be maintained as the room temperature. Then what happens is, we will feed that to the system and there will be a thermostat. Here there is going to be a thermostat which actually acts as the controller. To the thermostat we are going to feed that, yes, in the room there has to be a temperature of 22 degrees centigrade. Then the thermostats sends the actuating signals to the furnace wherein heating cycles will be performed. The heat will be generated and it will be released into the room vicinity. Then the temperature of the room raises. And here, even if there are external differences, That means even if the heat is breaching out to the room, or even if some cold breeze is coming inside the room, still that is also taken care over here, because what will be composed here is the room has to have a temperature of 22 degrees centigrades as per my requirement, that has been fed as an input to the thermostat. So thermostat sends the signal to the furnace. If suppose the temperature of the room is low, then the thermostat sends the signals to the furnace, yes Mr. Furnace, you need to work now. Then furnace generates heat, and this heat is released or liberated inside the room space. Then the room starts getting heated up, and the temperature in the room starts going up. Then the output is available. What is the output? It is the temperature inside the room. And this temperature, we expect that this temperature is as same as what temperature we fed to the thermostat. Now the temperature of the room is measured with the help of some temperature sensing device. The output measurement is carried out, and this temperature measurement with the feedback element is fed back to the thermostat, and in the thermostat a comparison of what we wanted, what temperature we wanted the room to have, and what temperature we actually got over here. This comparison will take place, and the difference, if suppose the room temperature is more, then the thermostat will cut down the heating cycles by sending signals to by sending instructions to the furnace. If the temperature is as good as we want it inside the room, then the thermostat continues the same number of heating cycles. Then if the temperature inside the room, the actual output measured, is lesser than what we desire, say it is about 20 degrees centigrades, whereas we wanted 22 degrees centigrades to be maintained inside the room, then what happens? A comparison will be taken care, 2 degree less, the temperature inside the room will be 2 degree less than what we want. Then what it does is, it sends signals or instructions to the furnace, yes Mr. Furnace, you need to work little more, and then furnace starts working. That is what is the mechanism, right? That is what is the plant or dynamic unit. Then the furnace is going to generate heat and liberate it inside the room, and the room temperature goes up. This keeps on repeating in every single cycle. Now the definition of regulatory system is what? The input does not build with respect to time. As the time passes on, the input, what we want from the system, that does not change. So that is what is here. See, whatever temperature, 22 degrees centigrades, it is never ever going to change. That is what is the input to the system. We want 22 degrees centigrades as the room temperature. That is what is the input. And with respect to time, as the time passes on, this input is not going to change. What temperature we want inside the room, it is not going to change. Right? That is why, since the input is not going to change with respect to time, over a period of time we don't change the temperature we want inside the room. So the input is not going to change with respect to time. And only thing that in this particular example, as the thermostats only regulates the heat, regulates the temperature inside the room, either by increasing the working cycles or heating cycles from the furnace, or by reducing the heating cycles from the furnace, or by maintaining the same number of heating cycles inside the furnace. What it is doing is, it is regulating the heat, it is regulating the temperature inside the room, whereas the input is not at all going to change with respect to time. That is why it is called regulatory system, because we are regulating the temperature. As per this example, we are regulating the temperature within the room as we want it, as the controlled output over here. Input is not going to vary with respect to time. So this is one good example of a regulatory system. We are regulating the temperature inside the room. Even if it is an open loop control system, and if a man is involved there, then it becomes manually controlled closed loop control system. There also, when man involves there, it becomes a closed loop control system, and the regulator of the fan could be acting to regulate the speed of the fan. That becomes manually controlled closed loop control system. Since there is no such manual intervention there, that is why we retain it as open loop control system. Now, this is what is about a regulatory system. Then, the second type of closed loop control system that we come across is follow-up system. Follow-up system. There are several examples. Just in the previous session, we took one example of missile launching system, wherein desired position of the missile launching, that will be decided first. Whereas, does the enemy aircraft stay at one single place in the space or in the skies? It doesn't do it. What does it do? It keeps on coming. It keeps on coming. That means at every instant, at every fraction of a moment, the position of the enemy aircraft will keep on changing. So accordingly, even your input position of the missile launching, the angle at which you are going to launch, the speed at which the missile is going to launch, that keeps on changing with respect to the speed, the position, the angle at which the enemy aircraft will be striking your territory. So because of which, that is also one such example of a follow-up system. Therefore, the definition of follow-up system itself says, ironical to the definition of regulator system, follow-up system is defined as, it is a type of closed loop control system wherein the input varies with respect to time. The definition of regulator system says, the input does not vary, the input does not build with respect to time, whereas in a follow-up system, the input varies, the input builds with respect to time. One more example is a lathe tracer head mechanism. See, this is an example of home heating system or room heating system. Example. This is an example. The regulatory system has been explained to you with the help of home heating system as an example. Now, here even in follow-up system also, we can illustrate the definition of follow-up system. What is the definition? It is a type of closed loop control system wherein the input varies, the input builds with respect to time. And we are taking an example of a lathe tracer head mechanism. The example of a lathe tracer head mechanism to illustrate the definition of the follow-up closed loop control system. So, let me write over here. It is a example, lathe tracer head. This is an example for a follow-up system. Okay. This is a block diagram that represents how the input is transformed into the output. This is a block diagram network, because writing a mechanism then explaining it to the viewers, it is going to be a daunting task because it takes too much time. As well, the complexity of the mechanism diagram, it will be so huge that the actual explanation will not be that easy. Because of which, we always write those who are learners of control system or control engineering, and those who practice the designing and planning of a control system, they need to know how to draw a block diagram network for any physical system given. So, this is the block diagram network which will demonstrate the working of a lathe tracer head mechanism. Now, what is this lathe tracer head mechanism? See, it is more or less similar to the application of jigs and fixtures. Right. What we tend to do is, in a lathe, if the number of products, similar or identical components to be turned on a lathe is very huge, right? 10,000 shafts need to be produced. In such a case, what do? Every time we want to turn the component by different profiles. In such a case, what we tend to do is, just like jigs and fixture mechanism, we make a tracer head, right? Tracer head. It is one of the attachment that will be mounted onto the movement of the single point cutting tool of the lathe. Right? This attachment, the tracer head as an attachment, it will be cut into a shape which resembles exactly which resembles exactly the path of single point cutting tool travel over the workpiece. That is why, since the single point cutting tool of the lathe has to trace the path that is to which the tracer head has been cut down, because of which we call it as lathe tracer head mechanism. So that after every single component, when fresh work material is mounted onto the lathe, then we need not go for the setting up of the tool position and then go for the turning, because the mounting of the cutting tool, setting up of the tool position, that takes away a lot of time. So in order to minimize that particular time, what we tend to do is, just like fixture, the lathe tracer head is mounted onto the tool post, so that the tool travel traces exactly the tracer head profile. Right. So now, if you would have got a brief idea about how the lathe tracer head would work because of whatever explanation I have just now made, now what you can see is, at every instance of time, at every fraction of a second, what will be the position of the cutting tool? It will be different, because say suppose, just for illustration, suppose if this is the path of the lathe tracer head, then at this, say at 0th second, just at the beginning of the turning, the tracer head profile is this. If at the beginning of the turning, the tool position is this, now after say 1 minute, where will be the tool position? It will be somewhere here. It will be this, it will be somewhere here. What does it mean? The input to the system, input to the cutting tool, that is the lathe machine, it will be like, at 0 instance of time, the position of the tool has to be this. Then the input, that is the tool position, after 1 minute, the tool position has to be here. What does it mean to say? The input to the system is the position of the tool. Input to the system is the position of the tool. So at 0 instance, at 0 minutes or 0 seconds, the position of the tool is this. Then after 1 minute, the position of the tool will be this. Forget about 1 minute. Even after 1 second, the position of the tool will not be here. It will be somewhere here. Why? Because the turning keeps on happening and the tool traces the path of the tracer head, because of which the tool will be cutting the raw material, trying to turn the raw material into the workpiece by removing the material from exactly the profile what has been shown with the help of the tracer head. So at 0 instance, the tool position is this. After 1 second, the tool position is this. After 1 minute, the tool position will be here. That means to say, the input to the system is the tool position, and the tool position is changing at every small instance of time. What does it mean to say? The definition of follow-up system, what does it tell? It tells that the follow-up control system is a kind of closed loop control system wherein the input varies with respect to time or builds with respect to time. So here the input is the tool position in the lathe tracer head mechanism. So at every small instance of time, the position of the tool is varying. That means to say, the input is varying with respect to time. So what does it do? The tool follows up the path as traced by the lathe tracer head. That is why it is called lathe tracer head mechanism. The tracer head will have been engaged to the path in which the tool, the single point cutting tool of the lathe has to travel. So since the tool has to trace the path defined by the tracer head, it is called lathe tracer head. And since the tool is tracing, what it is telling? It is following the path that is being traced by the lathe tracer head mechanism. That is why it is called follow-up system. And as per the definition of follow-up closed loop control system, the input, that is here in this case in the lathe tracer head mechanism, the position of the cutting tool, the input varies with respect to time. So here it is an illustration over here. See, reference input is, it is the tool position. The reference input to the system is tool position. Then tracer head with the stylus, it will have been attached to the tool slide, and then this, once you start the machine, then what happens, the cutting tool is going to trace the tracer head profile. So tracer head is going to control the movement of cutting tool. That is why the tracer head is placed here in the controller's position. Then the tool is tracing the tracer head part, that is why it is actuating mechanism, and then cross slide will be moving the cutting tool to turn the material, and then you get the controlled tool position, that is actual tool position. If suppose the cutting tool is deviating a bit, right, the tool position is diverging a bit or deviating a bit, then what happens, the cutting tool position will be sensed by the feedback in terms of the tracer head, and it tries to bring back the tool position again into the position exactly where, according to the tracer head, at that amount of time where the tool has to be in its position, that position is brought back for the cutting tool again. That is how the loop is getting closed with the help of feedback element, and even the input, when it varies with respect to time, that is also being handled. That is why, since the cutting tool is going to follow the path traced by the lathe tracer head, it is called follow-up system, and the definition says the input is going to vary with respect to time. Here the input is varying with respect to time. At every small instance of time, the position of that cutting tool is different. That is why it is called follow-up system. Then the third type of closed loop control system, it is called servo mechanism. Servo mechanism is a kind of closed loop control system wherein the controlled variable will be the mechanical position. Say some component, it has to turn, once I apply the load, it has to turn by say 30 degree, 40 degree. So change in the mechanical position, that could be the controlled variable you want from the system. Or you can also want some time derivative outputs, such as after applying the load, after applying the force, the speed of rotation, must be so and so, the velocity or the acceleration, that may be the output. So the servo mechanism is a kind of closed loop control system wherein the output from the system, the controlled variable from the system, it could be a change in the mechanical position, or it could be velocity, or it could be acceleration. One such illustration has been done over here. Say this is where the load is being applied. Say this is the gear which is meshed with the output from the motor. Now what is desired over here is some angle by which the component, the gear, has to be rotated once you apply the load. That is what is the intent. So what is the output that is desired? Position, the angle of rotation by the output gear element. This is what. Related to that, there will be a potentiometer sensing the movement of the gear to the desired position. Some voltage has to be generated. That is what is the system. Now related to that, the output will, the desired output related voltage will have been fed here to the potentiometer. Now what happens is, see, theta r is the desired output converted or translated or transformed into the what we want, the desired, the actual input to the system. So related to this particular output position, the input will have been fed here to the potentiometer, input potentiometer. So that is what is referred to as theta r. Theta r is the desired position of the gear. This is what is fed here. So related to that, the voltage will be generated. This voltage will be fed to the amplifier, wherein the signal gets amplified. This is passed on to the generator, and from the generator it is passed on to the electric motor. What is electric motor? That is it is a device wherein the electrical energy is transmitted or transformed into the mechanical energy in terms of rotation. So based on whatever electrical signal or voltage is given as a input, right, the motor will rotate the shaft, right, the motor will rotate the shaft by some angle, and the gear mounted on the shaft of the electric motor will rotate by some angle, and since the gear mounted on the shaft of the electric motor will have been meshed with the output gear, right, where exactly we want the tilting to take place or the movement, angular motion to happen, this is what is the gear, right. So, this gear when meshed with this particular gear, it is going to rotate the gear by some angle, and this is what is the output. This is what is the output that we want, that is where we want the output. So, that output gear rotation, that is what is the output, that is what is called theta c, that is controlled or the output rotation of the gear. Now, this related to the angle by which the output gear rotates, right, there will be change in the voltage in the potentiometer. This is called feedback potentiometer. This is the input potentiometer and this is what is the feedback potentiometer. So, now whatever output it is, whatever is the angle of rotation of the gear after loading, right. So, related to that there will be change in the voltage in the potentiometer over here. This is fed to the amplifier, and what the difference between what we wanted and what is actually available, that gets amplified, that error signal, the error voltage is amplified and it is given to the generator unit, and again the motor is going to rotate by some angle, and that is where this gear meshed with this particular gear is going to rotate, and that is what is going to give us the output. So, that is what is called the control. So, since here as you can see, as per the definition, it is a kind of system, servo mechanism is a kind of closed loop control system wherein the controlled variable is either mechanical position, that is an angle by which something could be wanted to be tilted, right, or maybe velocity or maybe the acceleration, right, that is what is applicable over here. As I had mentioned during the beginning of the session, any engineer who is involved in the design and development of a closed loop control system or any kind of control system, he need to know how to draw the block diagram network for any physical system given. Let us say consider the example of manual speed control system. Now, let me try to explain to you how the manual speed control system works. See, there will be some desired speed in our mind, that will be the input, and if it is a manual closed loop control system, then the human mind and the human brains will be the involved elements in controlling the speed, right. So, now let us try to write it directly. Say desired speed is the input to the system, right. Now, desired speed becomes the command input to the system, right. Then this is fed to the throttle position, accelerator, throttle. By what angle the acceleration must be throttled. Okay. Then this is given to the controller. Controller is what? Human element, and then what does the controller do? He sends signals to the hands, and then hands will actually take up the mechanism, and then what you get over here is the actual speed. Then this is sensed, the speed will be available in the odometer, that is seen by eyes, human eyes, and this will send the signals to the controller over here. Now, this entire thing is controller, and this is feedback element. This is plant or dynamic unit, and then this is command input, because this is what is actually desired, that has to be the command input, and this is what reference selector, right, and this is error detector. You need to adjust a bit your visual because I have no place to write here. Okay. Anyways, as I had mentioned during the open loop control system itself, the block diagram network, it will have command input, which is actually what you want, that is desired speed from manual speed control system. Then the accelerator throttle position is what is the reference selector. So you will be knowing by what angle, if I throttle the accelerator, this vehicle is going to go up in the speed or come down in the speed. And then the human being is involved over here. This entire thing is human being. Okay. So controller is the human being. So human mind will be involved over here, brain. Then whatever signal the human brain is going to calculate, those are implemented through the hands, right. That is what is the actuating mechanism. This is actuating mechanism, and this sends signal to the mechanism, that is the acceleration system, and what ultimately you get as the output is the actual speed. And this speed is visible to us because this will have been measured, and the odometer of the vehicle will be showing the speed, and your eyes, if it is human manual speed control system, the human eyes are going to look at the odometer and they will send the signal, what actual speed that will be seen by the human eyes, it will be sent to the human brain. Brain again calculates, compares the actual speed and what is wanted, and then whatever correction has to be done, this will be done. This is how you can draw a block diagram network for any either open or closed loop control system. Now, let me quickly run through the advantages and disadvantages of closed loop control system. In the advantages category, what comes is the disadvantages of open loop control system comes out as advantages in the closed loop control system. What? It is highly reliable. Why? Because there is output measurement, there is feedback, and there is correction happening in every single cycle, because of which this is highly accurate. Then it is highly reliable. Why? Because in every single cycle the output is measured and the feedback is happening. The controller is going to compare the actual output and what is wanted, because of which this is very much reliable. Then the external disturbances for any system, external disturbances in the open loop control system, external disturbances were not considered, right? Whereas here the provision will be available to overcome even the external disturbances. Why? Anytime there is external disturbance, it leads to the fluctuations in the output available, and due to the presence of feedback and the controller, because of which what we can do is, even if due to external disturbances the output is not the desirable output, then we can bring down the external disturbances, we can consider the external disturbances, and the applicable compensation can be made to the system, and we can bring back the output to the controlled output or desirable output. Those are the major advantages what closed loop control system carries. Then in the limitations column, obviously there are few limitations. What? Due to the presence of output measurement device, as well due to the presence of feedback element, the number of elements or the number of components are going to go high, because of which the system becomes complex. Then that means to say design becomes complex. Then due to the presence of those many number of elements, the sensors to sense the output as well as the feedback device, because of which what happens is the cost of the closed loop control system is going to be very high compared to the open loop control system. Then the third disadvantage, that is one of the most important disadvantage because of the closed loop control system, is that since in every cycle the output is measured and it is fed back to the controller, wherein the comparison of actual output available as well as the desired output that we wanted, comparison takes place and the correction is happening, because of which this will be suffering with the issues of stability. In every single cycle, the closed loop control system will try to correct the system and give you the controlled output, because of which the system is going to be suffering with the stability issues. Okay. Now, those are the major limitations with the closed loop control system. Now, let us try to put down the differences between the open loop control system and closed loop control system. Based on these many factors, we can differentiate easily the open loop and closed loop control system. OLCS stands for open loop control system, CLCS stands for closed loop control system. See, based on the output influence on the input, as per the definition itself, it says in the open loop control system, output does not influence the input because there is no output measurement, there is no feedback. So, what we can say is output influence on the input, there is no influence of output onto the input. Whereas here, because of the presence of output measurement as well as the feedback element, so the output will influence the input, because of which, yes, output influences the input. Then, output measurement, is it happening in open loop control system? No. In the closed loop control system? Yes. Then, feedback element, is it present in OLCS? No. Here? Yes. Then, accuracy, which system is accurate? This is less accurate, this is highly accurate. Then, reliability of the system, where can you rely? You can rely easily on CLCS, closed loop control system. Why? Output is measured, feedback is happening, and in every cycle, if there is an error, there is an effort to overcome that, because of which this system is, open loop control system is less reliable and this system is more reliable. Then, construction, open loop control system will have lesser elements, whereas because of which the construction is simple. Here, because of output measurement and feedback, the construction of the closed loop control system becomes complex. Cost, obviously this is low, this is high. Then, stability issues, open loop control system will face lesser stability issues. Why? In every cycle there is no correction, efforts to correct the system is happening, because of which the stability issues with open loop control system will be less, whereas here it will be more. Then, bandwidth, the frequency range between which the system can work. This works on lower bandwidths and this works on higher bandwidths. These are the key differences between the open loop control system and closed loop control system. Now, the next topic is, when will we call a system to be a good control system? What are the requirements for any system to be addressed as a good control system? Now, there are many actually, there are more than a dozen actually, whereas we will take up only those which are very, very important. The first one is the stability. Stability. Any system has to be stable, be it a human being, be it a mechanism, be it a machine, be it a vehicle. Any system has to be stable. It means to say, if suppose I drive the vehicle, say at 60 kilometers per hour, then every time I ride or drive the vehicle, it must be around 60 kilometers or just 10% here and there. That is addressed to be a stable system. Sometimes in a single ride, maybe from here, if I ride the bike or if I drive the car by about 1 kilometer, in that distance itself, if I try to vary the speeds, maybe at times I go at about 20 kilometers per hour and maybe at sometimes I go at 100 kilometers per hour, then my speed drive is not stable. Or let me put up like this. If suppose the vehicle for me, for 1 liter of fuel, it gives the mileage sometimes about 20 kilometers per liter, sometimes it gives only 80 kilometers per liter. Can I rely on that kind of a system? No, you cannot rely. Why? Because even if it is giving 20 kilometers per liter as the mileage, it must consistently give me only 20 kilometers per liter, so that I can estimate the amount of fuel before I take it up for any drive. If sometimes it gives 20 kilometers per liter, sometimes it gives me a mileage of 80 kilometers per liter, then I don't want such a system. Why? Because unstable, its performance, its behavior is unstable. So thereby what we can say is stability is a very important requirement for any system. And believe me, as per the recommendations from the professional controls engineering people or personalities, what they say is stability is considered to be most important requirement for any good control system. If and only if a system is stable, whether for underperformance or good performance, but it must be stable. If it is underperformance, then it must consistently underperform. If it is better performance, it must consistently perform better. It should not perform lower on one instance, and it should not perform better on the other instance. That kind of a system is called unstable system. So only and only if a system is stable, then only we will look forward for any other requirements for a good control system. Otherwise, we don't jump into any other requirements assessment. So what we tend to say is stability, that is why it is written as number one requirement, and if at all a system has to be a good control system or ideal control system, it must be very stable. Then the next requirement is the speed of response. You just imagine your braking system itself in the vehicle. Why? Because let us try to take only daily life examples, because the understanding of the concepts will be very easy. Braking system of your two-wheeler or a four-wheeler itself. What if the braking system of your two-wheeler or a four-wheeler is such that now if you apply the brakes, it will stop or it will slow down the vehicle after say 2 seconds or 3 seconds? What will you do that? Do you want such a mechanism? And it becomes very critical in some instances. Say suppose you are going on a road, a bus is coming from the opposite side and you are just behind some vehicle. Then suddenly the vehicle in front of you has applied the brake and it has stopped. Then if you apply the brake in your vehicle also, and what if there is a delay of even half a second, what will happen? You will end up into a mishappening. So because of which, as soon as I apply the brakes, the vehicle should respond and it should stop. What do you call that? Speed of response. The response time by the system to the input given, it must be almost zero. Within no time it should be responding. So that is what we call it as speed of response. So what type of speed of response do you want for a good control system? If at all a system has to be a good control system, then the speed of response has to be instantaneous. Or very high. Am I right? Then the third important requirement for any good control system is the accuracy. So the system, as much input I give it to the system, more or less the same proportionate output must be available. The transformation of input into the output must be almost the same. So what it means to say is the performance of the system should be such that it must be very accurate. Then number 4. The fourth important requirement is the bandwidth. The range of frequencies between which the system must be able to operate, that must be very wide. So bandwidth for a good control system should be very high. Oscillations. The next important requirement is the oscillations. Oscillations. So whenever we give the input due to any external disturbances, the oscillation of the system performance should not be there. So oscillations should be very low. Then one more very important requirement for any good control system is the sensitivity. What it means to say is any external disturbances given to the system, not given, it experiences. Apart from the input, the system should be very sensitive. So, a good control system has to be very sensitive. So, if we just assess the very important requirement for any good control system, if a good control system has to be accorded or addressed as an ideal control system, then it must be very stable, it must have instantaneous or very high speed of response or zero time speed of response, it must be very accurate, its bandwidth, it should be able to perform between very wide range of frequencies, that is very high, oscillations should be low, fluctuations should be low, as well as it must be sensitive to the disturbances. So, only then we will call a system to be an ideal control system.